Lesson: Data collection and preprocessing for predictive modeling. Data collection and preprocessing for predictive modeling are critical components in the toolkit of a certified AI-driven supply chain analyst. These steps ensure that the data used in predictive analytics is accurate, relevant, and actionable, thereby enhancing decision-making capabilities within supply chain operations. In predictive modeling, the quality and structure of data significantly influence the model's accuracy and reliability. Therefore, mastering data collection and pre-processing techniques is essential for professionals aspiring to harness the power of AI in supply chains. The first step in data collection is identifying the data sources that are most relevant to the problem at hand. In supply chain analytics, these sources can vary widely, including transactional databases, supply chain logs, customer feedback, and external data such as economic indicators. Selecting the right data sources is crucial, as using irrelevant or poor quality data can lead to misleading insights. According to a study by McKinsey Company, companies that leverage data analytics effectively can improve their supply chain efficiency by up to 15%. This underscores the importance of starting with the right data sources. Once relevant data sources are identified, the next step is data collection, which involves gathering raw data that will be used for analysis. In the context of a supply chain, this could involve extracting data from enterprise resource planning systems, customer relationship management systems, or Internet of Things devices. Practical tools such as Apache Kafka and Apache Nifi can facilitate this process by enabling real-time data streaming and collection. These tools allow for seamless integration of data from various sources into a centralized data repository, ensuring that data is readily available for analysis. Data preprocessing, the next step, involves cleaning and transforming the collected data into a suitable format for predictive modeling. This phase is critical because raw data is often incomplete, inconsistent, or noisy, which can adversely affect the performance of predictive models. Data cleaning involves handling missing values, removing duplicates, and correcting errors. For instance, missing data can be addressed through imputation techniques, such as mean substitution or more sophisticated methods like k-nearest neighbors imputation, which leverages the similarities between data points to estimate missing values. Another crucial aspect of data preprocessing is data transformation, which involves normalizing or scaling data to ensure that all features contribute equally to the model's performance. Techniques such as min-max scaling and z-score normalization are commonly used to bring data within a specific range or to standardize it, respectively. This step is particularly important when dealing with algorithms that are sensitive to the scale of input data, such as support vector machines or k-means clustering. Feature engineering is another integral part of the pre-processing phase. It involves creating new features or modifying existing ones to improve the predictive power of the model. This can be achieved through techniques such as one-hot encoding for categorical variables, feature selection to identify the most relevant variables, and dimensionality reduction methods like principal component analysis to reduce the complexity of the dataset. Feature engineering requires domain expertise and creativity, as it often involves identifying patterns or relationships in the data that are not immediately apparent. To illustrate the importance of data preprocessing, consider a case study involving a large retail chain that aimed to optimize its inventory management using predictive analytics. The company collected data from various sources, including sales transactions, supplier information, and economic indicators. However, the initial predictive model performed poorly due to issues with data quality and consistency. By implementing a robust data preprocessing framework that included data cleaning, transformation, and feature engineering, the company was able to significantly improve the model's accuracy, leading to a 20% reduction in inventory costs. In addition to technical skills, the role of a certified AI-driven supply chain analyst requires a deep understanding of ethical considerations related to data collection and preprocessing. Ensuring data privacy and compliance with regulations, such as the General Data Protection Regulation, is paramount. Professionals must be vigilant in anonymizing personal data and obtaining necessary consents before using data for predictive modeling purposes. Furthermore, the choice of data collection and pre-processing tools and techniques should align with the organization's goals and technological infrastructure. Cloud-based platforms like Microsoft Azure and Amazon Web Services offer comprehensive data analytics solutions that integrate data collection, pre-processing, and predictive modeling capabilities. These platforms also provide scalability, allowing organizations to handle large volumes of data efficiently. In conclusion, data collection and pre-processing are foundational elements of predictive modeling within the supply chain domain. By selecting appropriate data sources, employing advanced data collection tools, and implementing rigorous data pre-processing techniques, supply chain analysts can unlock actionable insights that drive strategic decision-making. The integration of practical tools and frameworks, coupled with a keen awareness of ethical considerations, equips professionals with the skills necessary to excel in the field of AI-driven supply chain analytics. As demonstrated through the discussed case study and supporting statistics, effective data collection and pre-processing can lead to substantial improvements in supply chain efficiency and cost reduction.